Mahsa Khalili is our next and final HeRo Trainee presentation for this afternoon. She is a doctoral candidate studying the assistive pillar under Michael Vanderloos. She's going to tell us about adaptive and modular technologies for wheeled mobility device users. Mahsa, are you here?
Yeah, but I can't enable my video. Okay, now it works. Great. Hi, everyone. As Kimberly mentioned, I'm Mahsa Khalili. I'm a PhD candidate at the School of Biomedical Engineering at the University of British Columbia. The work that I'm presenting today is a collaboration between researchers at the Advanced Robotics Systems Lab at UBC, occupational therapists at the International Collaboration on Repair Discoveries, and assistive technology developers at the British Columbia Institute of Technology in Vancouver. Next slide, please. Manual wheelchairs are the most commonly used wheeled mobility assistive devices around the world. And these devices are easy to maneuver, easy to transport, and also promote an active lifestyle. However, propelling a manual wheelchair is a physically high demanding task, and over time use of these devices may lead to secondary health conditions such as upper extremity, joint degeneration, and pain. More recently, there has been a surge in the design and development of modular power add-ons that can be attached to manual wheelchairs and provide on-demand power assist to users. Here at the bottom, you can see some examples of these power add-ons, including a rear end attachment, a front end attachment, and power wheels. Our collaborators at the Red Lab at BCIT are developing similar power add-ons with the focus on improving the modularity of these devices, as well as enhancing accessibility to different environments. At the CARES Lab at UBC, we are developing advanced control methods to optimally control these power add-ons with the focus on enhancing the autonomy of users, as well as improving the usability of these power add-ons. Next slide, please. To achieve these objectives, we are developing adaptive controllers that predict user intentions and provide appropriate assistant torque accordingly. Here at the top, we can see a combination of different wheelchair maneuvers, including left and right turns, as well as a straight propulsion. We conducted experiments and asked participants to follow these predefined paths at a self-selected and comfortable velocity, something similar to what they do in daily life activities. During these activities, we recorded the user input torque to the left and right push rims. And after this, after analyzing and filtering the measurements, we extracted relevant features from these kinetic measurements, and we used unsupervised classification methods to extract the implicit user intentions from these kinetic measurements. As you can see in the bottom graphs, the clusters that emerge from user push-rim interactions, which are also color-coded with the labels presented on the right side of these graphs, they represent different states of motion, or actually implicit user intentions that match with the actual wheelchair activities shown above. For example, the dots that are color-coded as yellow are related to when the user was actually doing a right turn, and we could correctly recognize those intentions by using these classification methods. And the intention estimation framework that we developed is computationally efficient and can be implemented in real time. Additionally, using this framework can contribute to improving power add-ons controllability and maneuverability when performing different daily life activities. Next slide, please. When using these wheelchair add-ons, wheelchair users can navigate a variety of indoor and outdoor terrains. Therefore, it's crucial to use and implement a controller that can adapt to different environmental conditions and changes. To achieve this objective, we conducted experiments in which participants were performing common daily life wheelchair activities on different terrains. We performed experiments on 3 indoor terrains of carpet, linoleum, concrete, and 4 outdoor terrains of grass, gravel, asphalt, and sidewalk. We instrumented the wheelchair with an inertial measurement unit sensor, or IMU, to collect acceleration and gyroscope data. We then use these kinematic measurements with a machine learning pipeline to first extract relevant time and frequency domain features, then to classify different terrain types. Our findings show that we can achieve high prediction accuracy when classifying indoor versus outdoor terrains. However, we found that the classification accuracy decreases when aiming to differentiate more similar terrains, such as a smooth concrete or linoleum. Currently, we're performing further analysis to improve this classification pipeline and using optimal parameters that can be used to actually improve the classification accuracy for a combination of different indoor and outdoor terrains. The proposed terrain classification framework is cost-effective and can be used for real-time control applications. And the classifier output can be actually used to adjust the power add-on velocity or torque on different terrains, which may as well improve users' safety and stability when using these power add-ons. Next slide, please. Yeah, you can find more detailed information about our work in the list of publications. And in the end, I would like to thank our research team and acknowledge the funding agencies that supported this work. Thank you for listening.